Here in this example, we'll be approximating sine x with, in this case, its order 5 Taylor polynomial. Right, so this would be t5, centered at 0. So we'll ask a couple of questions here. First, what is the maximum possible error in using this approximation? Second thing is, how would I use this approximation to find the sine of 12 degrees correct to 6 decimal places? And then the third question we'll try and answer is, for what values of x is this approximation accurate within 0.00005? So starting with the first question, what is the maximum possible error in this approximation? And in this case, focusing on just the range from negative 0.3 to positive 0.3. So in order to answer this, we could use the, instead of having to use the Taylor's theorem, we can use the alternating series estimation theorem. Because we know, according to the alternating series estimation theorem, we know that this is actually an alternating series. So for us here to use the alternating series estimation theorem, we can use it to try and find a bound on R5. So remember that the alternating series estimation theorem says that this is going to be less than or equal to the magnitude of the next term that would be in the series, which in this case would be x to the 7th over 7 factorial. And in this case, that makes it pretty easy, because now we can look at the range from, and actually here I should be careful, I should put absolute values on there. I can look at the range from negative 0.3 to positive 0.3, which means that the absolute value of x is between, or is less than or equal to 0.3, excuse me. So according to my alternating series estimation theorem, R5 would be less than or equal to 0.3 to the power of 7 over 7 factorial for x in this range. And at this point I can evaluate that on my calculator to get a better idea of roughly how large that error is. So if I'm doing 0.3 to the power of 7, and then I divide by 7 factorial, I get something around 4.339 times 10 to the negative 8. So actually a very small approximation. So, or I mean a very small error. I have about 7 zeros, 1, 2, 3, 4, 5, 6, 7, and then 4.339. Okay. So we see that here, just in this very small range, we know our approximation will be relatively accurate because of this very tiny error. How about the second question here, where we want to know what a good, or if I want to use this to approximate sine of 12 degrees correct to 6 decimal places? Well, let's figure out what we're actually going to be plugging into our polynomial. Because 12 degrees, notice, is not in the right unit. So to convert 12 degrees to radians, we'll do, we'll multiply 12 degrees times pi over 180. Right? So remember, that's going to convert our degrees into radians. Okay. So in fact, what we're going to be plugging in here is 12 pi over 180, which of course can reduce that a little bit. It'd be about pi over 15. So we can do pi over 15 for x here. And actually, checking in my calculator, I can see that pi over 15 falls within this range from negative 0.3 to positive 0.3. And certainly in this case, with an error this tiny, we know that our approximation will be accurate at least up to 6 decimal places. Actually, perhaps a little bit more accurate than that. So here we're good to just evaluate pi over 15 in our Taylor polynomial here. And that should be a relatively accurate approximation. And let's see, in this case we would have something about 0.207911693 and so on. Okay, so of course here we know that at least up to, for 6 decimal places, this will be a good approximation. And then for the third part, it asks for what values of x is this approximation accurate within 0.00005. In other words, we want to know for which values of x Rn of x will be less than 0.00005. Which we can now go back here to our error bound that we got using the alternating series estimation theorem. So let's use that here. So we know that here Rn will be less than or equal to absolute value of x to the 7th over 7 factorial. And we can just now find x for which this is going to be less than that desired error. So here, if I isolate x in this, we'll have the absolute value of x needs to be less than, let's see, 7 factorial times 0.00005. And then taking the 7th root of all that. So raising that to the power of 1 over 7 would give us a range that we can use for x. So let's calculate that now. So in my calculator, I get this is something around 0.82. Let's see, 82126. Okay. So in other words, for x within this range here, let's say as long as x is between negative 0.83 or sorry, 0.82. And positive 0.82. As long as x is within this range, we are guaranteed that our error is within this desired value.